drivers of later applications. And till now we were only using DFS and proprietary drivers, but we somehow persuaded our boss that open source is the way to go. And we thought that, okay, so we will take 9K, but there is no DFS in 9K. And our customers say, no way, we need DFS because for them, this is like for mobile application, it doesn't matter whether on which channel it stays. But for example, there are like big infrastructures that you need to get every dB out of a link. So you need to get maximum. And the plus of using DFS channel is high output power. So you can get the maximum what wireless can give. So we thought that okay, we'll go there, but we will need to implement. And we have been like studying this design concepts and contacting. Kati contacted us actually, and we thought that okay, we will go for it and try to get it forward. But we see now that it's kind of difficult because many people are not interested. On the other hand, we just don't have resources or knowledge about the whole Mac layer, how to get it through. So we will try to kind of give a bit of basics of DFS and how we see it can go forward. And then we hope that the audience will give comments and we'll start discussion so that we can go forward. So if you will explain something about basics.
So first of all, I get cold yesterday sitting in this fridge here. It's not loud enough, please let me know. So this is how I would like to explain what we have done and will do in the next few months. I will start with a short introduction of DFS basics to let all of us have a picture of what this all is about. Then the design concept for DFS module will be derived from the DFS basics. I will put some words on it there. From this concept, there are two major blocks. One is the pulse detector, and the second is the pattern matcher. I will handle them in separate chapters. Then some words to testing. And finally, how to integrate all this stuff in ath9k. So first, what is the purpose of all of it? It's basically to let Wi-Fi devices share channels that are normally used by radar devices. As core requirement that is set by the regulatory is just one little thing: do not operate in channels that are used by radar devices. Out of these core requirements, there are two functional requirements for your driver or device you have to provide. First is detecting radars, and second is manage spectrum based on your detections. Today there are three regulatories that define their specification for the regions, and basically all of them require the same. They differ in the parameters. And since for our application we have been only working on Etsy, it will, or in the reminder, it will be the regulatory domain we are discussing.
I just want to make one point out there on the last slide that those three regions are, or for regulatory domains for DFS, are essentially just used in different countries. Even if if it says FCC, you may apply FCC for different countries as well. And we did ask whether or not we foresee this to change, and apparently no. So if anybody does know of new changes like that, please let us know. But as far as we're concerned, these three regions are essentially the de facto that's used for APs for DFS.
That across the world.
Across the world.
Not just these regions, yeah.
Okay. So, for the first point, what is regulator requiring? It defines radar test signals with some characteristics. So first is a pulse width, then it is pulse repetition frequencies as called by ATSI, and the inverse of it is a pulse repetition interval that is used by FCC. I will maybe stick here to the second one because it's easier to just spell. Then there is a parameter given the number of different PRFs, and to place lastly the pulses from the burst. In the lower part you see a table for the single PRF. It's these radar signals you see. There are a bunch of different types differing in the PRFs and PPDs. So basically, what is important to understand here is there are radar types that just consist of 10 pulses, while there are others that are easier to detect because they consist of a much higher number of pulses.
One thing to mention that the regulatory won't test all of them. They will pick a couple of them from each type and test. Usually they do the tests like extremes, like for example, a lot of short pulses or really long sequences, for example. So they will just pick up some of them and use this as a test. So it's not specified how many pulses or what kind of patterns you have to put. It's up to actually test lab.
Okay, according to this, you maybe already see here that test signals are overlapping. So you might detect something that belongs to test signal 3, but also to 1. So in the end, it doesn't matter which test signal you hit, but you hit something. Then you're required to detect those patterns with a minimum probability, and for ETSI it's defined with 60%. So during certification you will get fired with quite some patterns, and you need to detect 60% of them in a defined condition setup. So the other part of the requirements is managing those information. So basically, you need to handle the channel state of each DFS channel. When you first start up your AP, all the channel states are unknown. To transform from unknown to available, you need to do a so-called channel availability check. Means you just start your access point without transmitting anything, and listening for 1 minute. That's what ETSI requires. After you didn't see a radar during that time, this channel becomes available and can be used. Using it means it transfers to operating state. During operation, you must do in-service monitor. Means constantly looking for radars. In case you detect something, the channel becomes unusable. And at the same time, you immediately have to move away from this channel, stop transmitting. Before doing so, you are allowed to do a channel switch announcement to let your stations disconnect from you. After a channel became unavailable, it is unavailable for quite some time. Here it is defined as 30 minutes as non-occupancy period that you have to keep. Meaning you, right from this number, you should not design your detector that it is generating DFS radar detections every some minutes because you run out of channels. After this non-occupancy period, a channel becomes usable and then again needs a channel availability check to get available again. Just for your information, these two values, after you detected radar, you need to move, and you need to do that within 10 seconds. And during this 10 seconds, you are allowed to have a 1 second aggregated transmission time on that channel.
So you don't have to switch right away. In old version, it was 250 milliseconds, which was kind of started to be real time critical.
Right.
And now it's 1 second, so it's a bit easier.
Okay. Now, out from these requirements, we can derive our design for all these DFS detection stuff. Basically, we have a detection module that is hardware or driver specific, and we have a managing component that handles all these channel states. You might need this NOL handling that is historically grown and means non-occupancy list handling. The other thing it has to assure is channel availability check times, and as said, when the radar is detected, inform your stations and switch as soon as possible to some other channel. Now for the detector part. When we first start working on this, or let's say that other than around, we start studying DFS from scratch and planned to have something that is available for all chipsets around. And we were told that there are some clever chipsets that just tell you that there was a radar. I'm not aware of them, but let's say they are existing. The other types of DFS detecting devices are those like Atheros ones. So they detect single pulses and forward them to the software to try to see some pattern. So for the reminder, I will assume the second one that we want to implement. And nevertheless, the interface to the management component remains the same for both of them. Now, I will describe or discuss shortly those two components. First one is the pulse detection. It is.
Go back for a second.
Yep. Question?
No.
This PowerPoint it will be available on our IQ.
Thanks. Thank you.
Okay. So what are the core functional components of the first part? It is to set up your pulse detection, to get them reported, and after, or as a pre-reporting step to the upper layer, you maybe have some clue of filtering out potential false pulses. And doing this post-filtering, you forward only those that you're pretty sure that were pulses. That's the first step, basically. And challenges for implementing this is you need in-deep chipset knowledge. Documentation for these functional blocks is, for good reasons, not available to the public.
I think it's patented even by authorities.
Yeah. And when you start working on that, you need a tight cooperation between the software part and the chip design. And therefore, it ideally has to be implemented by the manufacturer. What basically it is, and our approach to work on this module was first work out a GPL permitting NDA. Thanks for Kathy, it is done. Then try to find out how this pulse detection chipset is done and ported. And finally, as far as possible, try to port those filtering stuffs that prevent false pulse reporting. Current status is that we did this, so we ported the setup routines, and for a subset of functions we also ported post filtering that decreased significantly the amount of false pulses. Now to the next part, pattern detection. Pattern detection was relatively easy some years ago for ath9k. In version 1.4 of the recommendation, they used patterns defined with discrete values for those parameters I described. And now with 1.5 they moved to ranges. That means you cannot just take some predefined pulses and try to match with your pulses you recorded, but you need to vary all those parameters, meaning for the computational complexity you go full magnitude. So this has to be kept in mind when we are dealing with embedded devices with limited resources.
Yeah, I have a question now. So, are you required to support both 1.4 and 1.5 of the specification for ath9k for DFS, or moving forward is it everything just 1.5? For
1.4 is already required from April last year.
I'm sorry, can you say it again?
1.4 is already required for all new designs from April last year.
April last year.
And now what is as a law is 1.4 from some parts from 1.5. As in 1.5 is not totally in charge yet.
Thank you.
Okay. So from what you get from your pulse detection is what defines how you have to detect your patterns. And what you get is missing pulses, not in the word of missed, but all those pulses that you were not recording while you were sending. Then there are false pulses, pulses reported by the hardware that in fact were no radar pulses but some other interferences. And one factor that plays a role here is also the limited timing accuracy, depending on how pulses are detected. So the challenge here is identify pattern types that you will have to deal with, and then derive detection parameters you can work on afterwards. I will give only some examples on some of those detection parameters. Let's take our reference signal that is type 1 ath9k with simply n pulses PDF. First thing that will happen. Oh, sorry. Maybe one important information that is vital to understand. Missing pulses, as I said, is you missed some pulses because you were transmitting. And if you follow the requirements for testing, it is the channel load is 30%, meaning in the end you will lose some 50% of all pulses. Okay, what could happen? You could lose single pulses somewhere. So there are gaps, but those gaps are single gaps, and since you have a quite solid backed up information or you detected, you can just imagine, okay, there were 2 pulses, I can close this gap with a quite high confidence. Same is true for closing multi-gaps. So you have some single crease detected, then there is a gap, and then you see another single crease. Quite quite stable decision to say, okay, it was a radar. Something that looks easy, but in fact it's not. Imagine you missed every second pulse. So you're missing the information for your pre. For sure you can start speculating that, okay, it might be that I missed this, but in fact this would increase or make it impossible to handle this because of too many wrong radar events to detect. The next one is similar to that, but here we could maybe speculate it was a radar because it's the following. You see gaps of 1 and you see one gap of 2 missed pulses, meaning you can break it down to some greatest common divisor, and then you need to decide what are the thresholds I want to enable here to treat this as a radar pattern. Now I won't go into details and explaining what's with wrong radar pulses, but just by looking at those pictures you can imagine what happens if there were pulses that outside of this pattern, and you need to filter them out. All in all, it ends into this magical triangle. So you want a high sensitivity, meaning you want to detect as much as possible of true radar patterns. At the same time, you want a high tolerance, means you don't want to have false detections, or as little as possible. And to split them, you need computational complexity, so to cover all corner cases that might appear. To the testing, since the outcome of the pattern detection is a probabilistic value, you need a test set up for statistical analysis, and that's what we did. We generate the software or modules that first create patterns as defined by regulatory. Then we feed them into some false pulse generators, overlays all those true pulses with polluted ones. Then the next module just removes some of those pulses based on parameters you feed, and in the end all this goes to the pattern detector. This is how the outcome of this analysis looks like. We see at the top a well-balanced detector means or first explain what is displayed here. So you have your pulse loss probability put on the x-axis and the false pulse ratio put on the y-axis. Meaning here it would mean probability to lose a single pulse is 50%, while a value here means you will just add 100% to the pulses that your radar is on top. And now at the first image we see, okay, we are quite fine. We can detect up to 50 to 60% quite reliable, even with some false pulses here. If you look at the scale, 60% detection probability that is required by ETSI is yellow. So everything that is below here is good. And it means this is a good one. Plus, you see, this part is dark, meaning if you have basically no true pulses, but quite a lot of fake pulses, it won't detect anything. Contrast to that, the second one is too sensitive. Means everything is fine for detection, You see, it goes up to 70%. But if you have no pulses at all and induce fake pulses, you see it starts detecting something. We don't want that. So basically, this pictures you're able to guess your detector performance immediately. So it is good for you, but not relevant for the compliance stuff. Here you basically want to have your performance under a given or condition, lapse level term, and it would be just to evaluate this line, as I said, by 50% of probability to losing pulses. We do evaluate this by implementing a channel simulator that is based on ITU recommendation. This recommendation just works with a model to detect or to give listening and sending times. And what we did basically is replace the pulse loss module with channel simulator to have simulated testing lab conditions for DFS. And basically the output of those is your detector compliant or not?
Just as a remark, it's just when you go to the test lab, actually you can get certified completely useless device, which will get run out of a channel with 5 meters of operation. And for regulatory, it's okay, because you detect radar and you switch the channel, but this device is absolutely useless for the end user. You cannot operate on this channel, because you will be always waiting and switching to other channels. Okay, you have always no DFS channel as a backup, so in the end, somebody can certify a device which will just always jump to non-DFS channel, and then everyone is happy. But this we don't want, actually. So that's why it's all about this not oversensitive detectors, because it has to be also usable. Because you can easily calculate that if you lose each channel for 30 minutes, then it's a couple of detections, which is a day already will mess things up.
Now, everything so far has been simulated, but in the end we want to close the loop and test your device. How is this achieved? You have your device with those two blocks implemented, as I already discussed, and you just apply a radar generation device in front of it. So you fire some radar pulses at your device, and you should see that it detects something. Problem here when I was preparing the slides, I was assuming that here will be some independent developers, is that those DFS generating devices are not really cheap, or say, in other words, other people are buying houses for the price of those devices. So testing for a general open source developer is quite difficult. But with those two-tiered approach we choose, it is easy to bypass. So what you do is just set up your test environment, fire pulses, collect them, put it in a database, and then you can test your pattern detector offline. Now is the difficult part. We have implemented all those pulse detector and pulse matching routines already, and first we thought it would be quite easy to implement everything in ath9k and Mac. This is our initial proposal we posed. So ath9k has to be added some module that takes care about DFS. With those pulse detect, it sends them.
Yeah, this is actually not so easy because pulse detector, or let's say on Atheros chipset, the chipset is different. It would have to be kind of chipset dependent, but in theory it's possible. So you could have kind of a subset, not full implementation, but kind of subset you could use it for regression testing or testing your detector.
Correct. And Atheros will help with this piece. Will help generate real data through real hardware to create these profile databases per chipset, individual per chipset. And then that could be used for regression testing and all the other.
Now, the one point that I'd like to make here is that this likely is very dependent on the chipset, right, that you're using. So, you know, essentially vendors would have to come up with their own pulse detector profile databases of sorts if they want to actually use this, you know, economic way of doing DFS testing.
Right. Actually, we would like to know how other vendors are doing, but we don't know.
But then you're also missing the piece of the, if there is a DFS even separately and talking about those same keys, that needs to be put together.
Yeah, I mean, this is implementation. This is original, like initial idea, open for discussion.
That's just for us to see if this could work. And as Wojciech said, if this worked and people would agree that this is